своего аппарата на YouTube и смотрит, пошла трансляция.
Oh, sorry. So we'll continue in English. This will be a course in algebraic geometry, and I will regularly send the home assignments. So please make a list of your emails. Then I will send you home assignments. If it's not enough, we'll have more. I will follow the book by George Kemp. Called Algebraic Varieties. And it will certainly take up the whole fall semester and part of spring semester. And then when we finish with this book, we'll see how to continue. But so far, we'll just literally follow this. You are very welcome just to read it by yourself and skip this class altogether. Well, maybe some exercises will be not of this book, but otherwise all the presentation will be literally following Kemp. Okay, but in the very beginning I will say a few words of my own. Algebraic geometry in the beginning will be followed upon differential geometry that I hope you have some knowledge of. So just smooth manifolds, varieties. In differentiable geometry. They come in two incarnations. Historically, first is a sort of global approach. Maybe due to Poincaré, or even before that. Sub-varieties in some big affine spaces, just given by a system of equations. And then you somehow apply theorem on implicit function or something like this. Smooth subvariety. Somehow this existed before in 1913 there appeared a local approach due to Hermann Weil. So M is glued from some atlas. Or maybe this ball is also isomorphic to RK, but usually, at least you imagine it as a ball, as an open ball. Okay, so you have one ball, another ball, yet another ball, and they all intersect somehow and cover the whole M. And I presume that you know this all very well, yeah, from some algebraic, analysis on manifolds course or something like this. Somehow it's rather striking that the people studied manifolds, varieties for a long time before this modern definition appeared, and quite successfully. For example, 30 years before this, Wilhelm Killing classified all the Lie groups, but it's even hard to imagine what exactly he proved without this definition, because Lie group is a group on a manifold, on a variety. But then how do you identify them? Because how do you identify two things like this? They may be embedded in two different ways, in two different spaces, and then how you prove that they are, or even how do you define that two are isomorphic? So in one, it is difficult to define isomorphisms. And more generally, morphisms. So that's why people need this other approach, the local one. And then in the local one, everybody knows how you define morphisms and isomorphisms. Okay, now we will sort of follow this pattern for algebraic varieties. And then probably, again, everybody knows what an algebraic variety is. So we'll have a base field. So it will be at least algebraically closed, and for the most part it will be just complex numbers. But then it could also be, say, an algebraic closure of a finite field, so of finite characteristic. And then many things are strikingly different over finite characteristic. But in the beginning, when we just work out definitions, the definitions will work for all the algebraically closed fields similarly. And then, well, you know what is an affine space. It's just k to the power n. And then I bet everybody knows what is an affine algebraic variety. So maybe somebody can tell me what is an affine algebraic variety. Again, similarly to this situation, so from this point of view, any smooth manifold is sort of affine. Yes, absolutely right. So affine algebraic variety. Say M inside a n is cut out by a few polynomial equations. Okay, and this is somehow a version of official definition, but again it's very hard to work with, because even we can have two lines in the plane, so it's A2, and this is one line L1, and there's another line L2. So we're given by equations AX plus BY equals C, or say DX plus EY equals F. Okay, and these are different equations, but the lines are certainly the same, and both are isomorphic to just one-dimensional affine space. But somehow we have to have a language which allows us to identify different, at least differently looking algebraic varieties. So problem different systems of equations, polynomial equations, can cut out isomorphic algebraic varieties. So how to define isomorphisms? And more generally, again, morphisms. And we need morphisms to consider not necessarily affine algebraic varieties, because arbitrary varieties are again glued as before of affine varieties. For example, like P1 is the union of two copies of A1, the union over the punctured A1, or like say multiplicative group, and then we have to define some morphisms from intersections to bigger varieties and things like this. So we desperately need the notion of morphisms, and with this global definition as closed subvarieties in a affine space, we don't have. It's impossible to have a notion of morphisms that one can work with. Okay, so we need some other definition. So to this end, one needs another local definition. Okay, and this is what we will start with. And this local definition will be a sort of a ringed space. Space locally looking like an affine algebraic variety so in the previous global definition. Okay, so let me say a few words about ringed spaces. We'll in fact, for following Kempf, we will not consider the most general ringed spaces like Grothendieck did, like schemes. Well, we will, but maybe in half a year. But we will start with varieties which are more suitable to usual intuition. So we'll have X a topological space. Equipped with well, let me say this word, sheaf of regular, so to say, functions. And now please raise your hands, or just one hand, if you know what is a sheaf. So just literally everybody, but you don't, and you, so every, okay, sorry, raise your hand if you don't know what is a sheaf. Okay, so let me review. So sheaf on a topological space X is the following thing. So each we associate to each open subset in the space of sections. F of U. So F is our sheaf. And this F of U may be just a set or an abelian group, or in our situation, because everything is over a base field K, it's just a vector space over K. K vector space. But more generally, once again, it could be an abelian group or just a set. For many constructions, you don't need more. And then we have the following requirements. So restrictions. First of all, you can restrict sections. If U prime is smaller than U, then you have restriction from U to U prime. Okay, and then somehow that's the whole data. Well, maybe you need some transitivity. When you have U prime inside U, U double prime inside U prime inside U, then you can restrict in two ways. Okay, and this is the whole collection of data, but now they have to satisfy certain requirements, and this requirement is locality. Suppose that some open set is covered by a few smaller subsets. So U is union of smaller subsets, and then you have restrictions of sections from here to sections over there, and each section is uniquely defined by those restrictions. Well, let's say it's finite, not to have theoretic difficulties. So you have a map, restriction map from sections on U to the direct sum over all alpha of sections over these subsets. And this is an embedding. So each section is defined by its restriction to smaller subsets if they cover the ambient open set, and somehow you can, so that is an embedding, and you can describe the image. Yes.
Пропущено U и U', то есть в одном месте там должен быть U', а в другом должен быть U.
Where?
На вот этой доске. У вас, соответственно, ограничение.
U to U prime.
А при этом...
Oh, sorry. Yes, pardon me. No, that's okay? Oh, thank you. Sorry. Okay, and now the image is the collection of local sections on these open subsets that coincide on the intersections. Maybe let me write it down. Here?
Ограничение пишется сверху вниз, правильно? Или...
You want me to switch prime?
Мне кажется, что ограничение сверху вниз, нет? При импульсе.
Like this? No?
Может, я не прав?
I have no idea. Let's be this way.
А еще вот там точно хватит для конечных аксиомы?
We'll only use it for finite coverings in algebraic geometry. Okay, so the image consists of the collections of local sections, such that for any pair alpha and beta, the restriction, let me write it this way, f alpha restricted to u alpha intersect u beta is f beta restricted to u alpha intersect u beta. Okay, so to two very natural conditions, and they can be labeled by intuitive word locality. Okay, so the basic example. Of a sheaf f of u is what? So say, Vanya, what is your favorite?
Constant. Local.
Okay, but that's indeed basic, but maybe not most simple. What is most simple? Functions, right. Just all functions. Really? And what did I miss?
Существует глобальное сечение, которое ограничивается на эти f-вали.
I described the image. So the image consists of, I think, right?
Сказано, да?
Yeah, it's written down here. The image consists of the collections f alpha such that they coincide on intersections. So the global sections on U can be reconstructed as compatible systems of local sections. Okay? Okay, all functions from U to say our base field K. Okay? Or say since we had topological space, then all continuous functions are also good. Yes?
But this is a pressure.
This is a pressheaf. I think that it is a sheaf. In fact.
In your definition.
In my definition, if I only have this part of data, just a functor from open sets to sets or anything else, it's a pressheaf. But with this condition of locality, it is a sheaf. So a sheaf is a pressheaf like this, with this condition of locality.
Что такое f-альфа маленькие?
Just sections f alpha in f of u alpha. such that, okay. Okay, so once again, the constant sheaf is a very good example, but at least intuitively, it is somewhat somewhat less intuitive than this one. This is absolutely basic, and in fact, this is all we will need for time being. Okay, and now I can. Well, this was a definition, a very important definition. And now another definition of an space with functions. Maybe a space ringed with functions. So it's a topological space. X with a subsheaf OX in the sheaf of functions, of continuous functions. Pardon me? Yes.
Мне кажется, все-таки для того, чтобы все определить пучок, мне кажется,
Yes.
еще одна стрелка.
Yes.
То есть у нас есть стрелка из фу в сумму, мне кажется, там должно быть еще пересечение. И это должно быть точно...
Oh yes, but that's what I said in words. I could also, okay, let's write it here and then erase it. So you have f of u goes into the sum of f of u alpha, and then goes to the sum over alpha beta and a f of u alpha intersect u beta, and also let's write 0 here, and this must be an exact sequence up to here.
А точность в среднем члене какой, эквивалентно какому утверждению в определении пучка?
The description of the image, or what do you mean? Exactness in this term, just that this is an embedding, and also, well, the map to here is, well, it takes. Yeah, so here you have some, maybe you have to order them, and then you will take one restriction minus the other restriction. Okay?
Можно вопрос?
Yes.
У вас написано, что f альфа принадлежит f от альфа, но
Yes.
по сути векторное пространство это вектор.
Yes, absolutely.
Значит, вектор ограничен на открытой возможности.
This is by definition. The restriction from u beta to u alpha intersect u beta over f beta. Okay? But I think that this way of writing is intuitively clear, or even more clear than that. Yeah? Okay? Okay, so
Это
Точное последование к чему относится?
This was just a short way to write what I wrote before in words. So it's ringed with functions, a topological space with a subsheaf, and then OX of U is called regular functions on U. And it's up to us to specify the notion of regular functions. For example, all functions. Or just continuous functions, or maybe constant functions, I don't know. It's up to us. But then it will lead to different notions of ring space on the same topological space X. Okay? And once again, this choice is important, and we have to specify it each time we speak about ringed space. So it's a sheaf, and when we need one extra condition, such that for any function f, a regular function on this open set U, certainly its zero set is closed because maybe I didn't say that it's necessarily continuous. Maybe I should say that I did say that it's continuous. Okay, so the zero set is necessarily continuous. The f is f inverse of 0. It's closed. And df is the complement to this closed subset is open. Okay, and so in particular, it's equipped with its own space of regular functions. Okay, then the condition is that 1 over f restricted to df is a regular on df. Pardon me? The functions are with values in the base field K always. Pardon me? No, we don't consider topology on the space of functions. We only need topology on the space X itself.
We are talking about continuous functions to the field.
Okay, sorry.
Мы не требовали непрерывности в определении.
Yeah. Okay. Let's then erase this, unless our field is complex numbers, and then I need to ask that this is closed and the complement is open. So this is a requirement. I require that the zero set is closed. Okay, the complement is open, and of this complement, the inverse function is regular. Okay, these are all requirements. So I require this, I require that.
Почему плохо требовать там, чтобы были непрерывные?
Because we have no topology on K in general, yeah, and so what do we mean by continuous functions?
But K is an algebraic space of dimension 1, thus we can consider continuous function.
Just say if K is algebraic closure of a finite field, then what?
Zeriski topology on it.
Yeah, but so far we didn't define Zeriski topology. We will eventually, maybe even today, but not yet. So,
Мы сейчас не требуем никакой непрерывности.
no, somehow we don't have
Даже для C.
any. Well, for C we can impose such a requirement. We can. But yeah. But maybe let's not use the topology of complex numbers. Though if it's easier for you intuitively to think about it, you are very welcome. Yeah. Anyway, over complex numbers, all our functions, all our regular functions, eventually will be definitely continuous. Okay. So you can think of them as continuous functions.
А регулярное значит многочисленное, да?
No, it means nothing. It's
Слово регулярное.
it's just
Это название.
yeah. So we'll consider ring spaces. We will name the space of functions regular functions. It's our terminology. Okay, because we consider arbitrary functions, but we will need. Okay. Okay. So. Did everybody inscribe in this list? Everybody, absolutely, yeah? You did not? Please do, and return it to me. Okay. Okay. Now, this was our definition of ringed spaces, and next definition is a morphism. Maybe I should also add that that is really a ring, so that OX of U is a ring. So we can subtract and multiply regular functions. Okay, or in fact, since we live in vector space over K, it's not just a ring, but it's a K algebra. Okay, so the next definition is about morphisms. Between ring spaces. So we have one ring space X with its ring of regular functions, and another space Y with its ring of regular functions. And what is a morphism? Say pi. So first of all, it's a continuous morphism between these topological spaces. From X to Y. Okay, and now as such, it defines the pullback on functions. All right. So if you have say an open subspace V inside Y, then you have this morphism from X. So you have U that is the preimage of V. Okay, and you can pull back your functions. So for any say function G, regular O Y or V, regular function in terms of Y, you can consider its pullback pi upper star G. So it's just the composition of G and pi, and it's a function on U, and we require that this is regular. Okay, so B is some data, and B is some requirement on this data. Okay, so this is a morphism, and well, maybe let me formulate the property of locality of this notion. So suppose we have a covering X is a union of U alpha, and Y is the union of V beta, and the morphism pi sends each this covering to an open space in the Y covering. Okay, then pi is a morphism if pi restricted to U alpha is a morphism for any alpha. Okay, so you can check this property of being a morphism locally.
But we have
Yes.
morphism from X to Y only defined.
Yes.
Morphism from U alpha or
Well, we have defined a very general notion of morphism, right? We can apply it to everything.
we are applying morphism to locally to ringet with functions space. Yes.
Oh yes, but well, certainly you can restrict to opens. Maybe I should say it explicitly. Okay, let me say it. So if U in X is open, then O X restricted to U is well gives well supplies U with a structure of a ringed space. Okay.
That's actually my question.
Thank you. And then I implicitly used this what Anton just asked in my locality property. Okay. So still, this notion is very useful, but is too broad. Inside those ringed spaces, we have to specify algebraic, so to say, ringed spaces. Let me give a definition. I say that Y or Y it's a ringed space is an affine algebraic variety if first of all the global sections of Y just the global sections of this the global regular functions form finitely generated K algebra. And it's also denoted by this. So these are the same things. And what does it mean? It means that, well, there are finitely many generators, like x1, or maybe f1, and so on, fn. These are finitely many generators. Now we can form absolutely arbitrary expressions among them, and this will be the polynomial algebra in n generators. Okay, free polynomial algebra, and it surjects onto k of y. Okay, and the kernel is some ideal, and I hope everybody knows what an ideal is. Yeah, and maybe even everybody knows the basic Hilbert theorems. We will recall them next time, but still Hilbert basis theorem, yeah, everybody knows. Hilbert Nullstellensatz. Maybe raise your hand if you don't know Hilbert Nullstellensatz. Great. And do you know Hilbert basis theorem? Do you? Okay. Anyway, we'll recap it next time. But there is some ideal inside. This is just another name or symbol for this algebra of global regular functions. Because it's commonly used in algebraic geometry, so you may.
Нам давали общее определение, мы не требовали, чтобы этот лист его алгебру, мы требовали только векторное пространство, да?
But then at some point I wrote here that the regular functions must form a ring. You can subtract them, add them, multiply them, so it's always an algebra. In particular, there's an algebra of global regular functions. And this algebra must be finitely generated. But that's not all. That's not all, because there is a second condition that I can take some other ring space, test space, and then I can consider all the morphisms from x or x to y or y. Okay? The morphisms from a ring space x to the ring space y. And in particular, they act somehow on the global regular functions. Yeah, so from here there is a map to morphisms from k of y into k of x. Yeah, just pardon me?
It's algebra homomorphisms.
Yeah, just these are homomorphisms of algebras. But by definition, maybe I should say more alg, something like this. Okay, so now the requirement is that this is an isomorphism. That all the morphisms from x to y are uniquely reconstructed from their action on the global regular functions. Well, it's an abstract definition. Well, at least we gave some definition, and it will be easy to work with somehow. Yes.
We can have two same space, but say that they are different for or no. It's for all x.
For any ringed space X, the morphisms from X to Y are uniquely reconstructed from their action on the global regular functions.
Z bijection, yes?
Yes, absolutely, yes. So this is our definition. Okay, so then we'll spend the remaining 10 or 15 minutes and the whole next class in a week proving the following big theorem. Any affine algebraic variety is uniquely reconstructed from say what y or y is uniquely reconstructed from its она сама-то в маске? Pardon me? Oh, but then maybe it's better to open a window. From its ring algebra K of y of regular functions. Okay, and this K of y is, as we saw, a quotient of the ring of regular functions on the affine n-dimensional space, and so this y is really a closed subvariety in affine n-dimensional space. So we end up with the initial approach. Yes.
And if we have like zero algebra with only one element, so we have no...
Like K itself, yeah? Or what? Or just zero algebra? Maybe we don't consider non-unital algebras, we only consider unital algebras.
K algebra, so it can be different spaces topologically. But it's unique up to morphisms.
Up to isomorphism, yes. Is uniquely reconstructed, so up to an isomorphism.
So it can be different topological spaces, for example.
No, an isomorphism certainly is identifies the topological space, the underlying topological space.
But imagine we have only constant functions.
Yes, I can imagine this.
But we can have a constant functions on different spaces, and they have.
They will not be affine algebraic varieties. Yes. Pardon? Say Masha. Yes.
It's actually a big theorem because if we say that the morphisms are I believe that the statement that we have is an equivalence of factors.
Yes, absolutely. Between algebras and affine algebraic varieties. Yes.
We have a big theorem that this is an equivalence of categories, and we have a definition that this is an equivalence of categories. So something is really wrong.
Нет, в смысле,
No.
вроде все понятно, если мы докажем, что существует, это тоже понятно.
Yeah, the question is, do they exist?
Yes. Yes, the question of existence, absolutely. The question of existence, yes.
Что вся величина теорема в том, чтобы дать такое определение.
Yeah.
Ты удаешь, что становится тривиальной ему дать. Нет, реально додуматься до такое определение, но как только ты его даешь, утверждение очевидно.
So there's an equivalence of maybe
Вопрос про то, что оно изменение лишает, видимо, речь наоборот, просто для любой алгебры существует.
yes.
Не то, что у нас не может быть одно кольцо и две схемы, два многообразия, а у нас не может быть для каждого кольца есть многообразие. Вопрос вот этот.
Yeah, there are some questions.
Как будто проблема в том, что у нас может быть два многообразия и одно кольцо, а проблема наоборот, что у нас...
Такая проблема тоже.
Вы что раз видите констанцию, то вы знаете,
Почему? Нет, так, поэтому мы можем переобразоваться состоит. Может быть, два кольца, одно кольцо и два многообразия.
Maybe we need not reconstructed form, but constructed by algebra, not reconstructed form, so we already...
Okay, but maybe these are sort of psychological questions, and let's refer to psychologists. But you have some questions with the same. Okay.
When you are writing reconstructed form, it means that we know that it exists. Yes.
Yeah. Okay. So let's start with something, namely just with a fine line. This will be our first basic example of a fine algebraic variety. A1. So as a set, it is just our field, and now we need to specify some topology, and this is called Zeriski Topology. Namely, the closed subsets are finite by degree. Okay, we declared that the closed subsets are finite. Okay, that's our definition. Fine. And now, what about regular functions? So we have an open subset U. U is K without some closed subset. So say x1 and so on, xn. And now I have to say what is the ring of regular functions. Well, they're just rational functions on this line with possible poles in these bad points. But so they're regular away from these points, but may have poles at these points. Okay, so these are functions. Rational functions. Like one polynomial of z over another polynomial of z, but this other must have zeros only at these points, so it must be of the form product z minus x I to some power, like di. Yeah, this is the definition. In order to specify a ringed space, we have to specify topological space and the sheaf of regular functions. So here I specify the sheaf of regular functions. I did it. Okay, now what do I have to check? So locality, I think, is evident. Yeah, because you see it's a subsheaf of all functions, and all functions do form a sheaf. And there was one extra property, if you remember, yeah? So if you have a function, f, then the zero level set must be closed. So is it true? In our definition of closed, because any function can have only finitely many zeros, right? Because this is a polynomial.
Well, okay, maybe a zero, but it's close to.
Right? We're in some open subset, the complement to these poles, but then this is a polynomial. It has finitely many zeros, so we're there.
Zero, but
Okay, and then we must also check that df, this is the complement of u minus f inverse of 0, and 1 over f is a regular on df. So now we already do have the notion of regular functions, so there is something to check. And can we check this? And how?
1 over f is by definition a function defined on.
Here. It is defined here, just point-wise.
Of multiplication. Okay.
Yeah, you use the multiplication division in k in our field. So everything is well defined. So why is it regular? So why does it have a similar?
Because it's a rational function.
Yeah, because again, a rational function, and it may have poles now in zeros of this guy, but then we removed these zeros. So we checked this. Okay, and now we didn't prove really that it's an affine algebraic variety because we didn't prove this. Right? And to prove this, we have to know what are morphisms from polynomial algebra in one variable to any algebra at all. So I have this algebra k of x, and what are morphisms from the regular functions k of a1, and these are just polynomials in one variable into k of x. What are they?
We need to just
I mean algebraic morphisms. No, we just have one variable.
k of x.
Yeah, because it's a free algebra, so we're absolutely free to send z anywhere we want. But then everything is reconstructed from this. So it's just k of x itself. Namely, morphisms goes to the image of z. Okay, fine. And what about the morphisms of ring spaces? So again, well, we do have again a morphism from here to k of x, right? Because we just given a morphism, say pi, it goes to pi star of z, yeah, right? But we have to check that this is an isomorphism. So why it is an isomorphism? Huh? Nice, yes, and how? Though somehow we have to stop now. So maybe yes, but why? We have to prove this.
Ну, то есть вот у нас есть условия на функцию. И это как раз таки те условия, которые нам заставляют морфизм быть непрерывным. Но рано впечатление.
Okay, so it's not difficult, but I will include it into home assignment. Okay, so I apologize for a very short lecture today. Hope for the next time it will be better, but who knows?
Maybe
So
say something about homeworks and other.
you mean the grading of the course or what? Yeah. You are absolutely right. Thank you. So for some technical reasons, in this how is it called? PUD. I don't know how it's the name in English. I have to use the final exam, but in reality there will be no final exam, and everything will be graded just by your home assignments, just by percentage of the home assignments you solved, and you can just bring your home assignments to me next week or send it to me. But if you send it to me, then it must preferably typed in TeX or whatever. So that it's very clearly written. Because if it's say a few pages in random order, I will just discard it. Or if it's handwritten, so I cannot read it, I will discard it either. But if you prefer to write it down by hand, then just bring it to me next time, like this. And I think that's it. Thank you. Да.
Чуть непонятно. Там в итальянской категории кажется, что мы определяли как пучок функций, чтобы у нас функция однозначно восстанавливалась по ее значениям.
Да, конечно.
Тогда, кажется, в алгебрах надо требовать, чтобы они были безнипотентны.
Ой, прошу прощения, надо было, безусловно, надо было сказать без нильпатентов. Да, я прошу прощения, да, это я забыл.
Еще раз, мы определили афинную как ту, где морфизмы, ну, как вот это, да?
Ага.
Сейчас. Отсюда очевидно, что не бывает двух